Welcome everybody. Thank you for taking the time today to join us in this webinar. I'm Gabriella from Image Reality. I'm joined today by Peter Gutteridge from Cambridge Carbonates Ltd, who will be taking us through and leading us on this webinar. There will be a section at the end for question and answers. There'll be time for that. So we will take questions then. But if you have any burning question right now as Peter goes through the webinar, please take the opportunity of typing it into the comments box on the platform you're using, maybe using LinkedIn or YouTube, and we will certainly have a look at those questions at the end and put them to Peter. Peter, thank you. Over to you.
Thank you very much, and good afternoon to everyone from the UK. I'd like to present this webinar on Cretaceous sequence stratigraphy and palaeogeography of the Arabian Plate. The aims of this webinar are to look at the Cretaceous petroleum systems using our regional palaeogeographic maps. We have a series of third order sequence and systems tract maps from the whole of the Phanerozoic. This is an example of one of them. This shows the high stand systems tract to the K180 maximum flooding surface of late Campanian age. It covers the main economic area of production from the Arabian Plate, covering Iraq through Kuwait, the Gulf states, down to Oman and up to the Zagros Suture. And within this, I want to focus on 4 case histories in carbonate and mixed-clastic carbonate settings. And I will be expanding on these case histories and presenting more case histories in a remote workshop I will be running on the Cretaceous petroleum systems, presented jointly with Image Reality on Stratbox on 30th of October through to the 3rd of November. Let me give you some history and workflow of how we construct these palaeogeographical maps. In 1992, Cambridge Carbonates undertook a sequence stratigraphic and palaeogeographic mapping of northern Iraq. In the period 1992 to 2000, we extended this stratigraphic scheme and this palaeogeographic mapping to all of Iraq. And in 2000 to 2001, my co-author, Andrew Horbury, who must take credit for pretty much all the regional work involved in these maps, was invited to be a co-author on what's turned out to be an industry standard publication on the Arabian Plate sequence stratigraphy. And since then, all our focus has been on updating and extending this palaeogeographic mapping to the Gulf states and up to the Zagros Suture. So each of these maps is based on a robust sequence stratigraphic framework. It's based on the correlation of plate-wide third order maximum flooding surfaces with the terminology of K10 to K190. We have incorporated published lithostratigraphy and time stratigraphic information, including biostratigraphy and strontium isotope stratigraphy. And our original interpretation, compared with 2001, we have expanded the number of Cretaceous sequences from 19 to 30. And for each sequence, we have a map of low stand systems tract, transgressive, maximum flood, and high stand systems tract. And then we built in the sedimentological information based on published data from outcrop, core, well logs, seismic geometries, and we posted these on base maps to come up with the palaeogeographic maps. And each map is identified according to the maximum flooding surface that third order sequence contains. If we look briefly at the Cretaceous plate tectonic setting, from late Jurassic to late Cretaceous, the Arabian Plate was roughly in an equatorial paleolatitude, and it was essentially a passive margin formed along the southern margin of the Neotethnian Ocean, which was opening for much of the time until the very end of this period. From the late Cretaceous to the early Cenozoic, Neotethys began to close, and we begin to see evidence of structuring and ophiolite abduction along the continental margin. We don't actually see the continental margin and the preserved Arabian Plate because that was consumed by the convergence culminating in the Zagros development of the Zagros Suture. If we look at the overall controls on Cretaceous deposition, this is an overall Isopac of the Cretaceous, and the thickest Cretaceous is along the Zagros suture, up to 10 kilometers thick locally, and also along the Rub al Khali Oman mountain axis, and it thins to zero by onlap against the Arabian Shield. And there are also major depositional highs controlled by underlying basement structure in the Fars province of Iran and along the Hail Rutba arch in northern Iraq. So this is the stratigraphical architecture of the Cretaceous. This chronostratigraphic diagram really covers Iraq, and it's derived from the Geology of Iraq publication, Akrawi et al. 2010. And I've also added on the marine strontium isotope curve and the first order sea level curve schematically. And the Cretaceous comprises two megasequences, AP8 and AP9, and this has been split into 6 supersequences, each of which rests on a major unconformity. And these sequences onlap the Arabian Shield to the west, and in the lower part of the Cretaceous, there's a great deal of clastic input from the Arabian Shield, resulting in the development of these mixed-clastic carbonate systems. Essentially, from the Barremian to the Aptian, this was a passive margin, and these unconformities correspond with a series of tectonic events, generally linked to the various stages of opening of the mid-Atlantic, and also various episodes of thermal doming on the Arabian Shield. So the framework for Cretaceous deposition, we have to go back to the end of the Jurassic. In fact, the earliest Cretaceous megasequence actually starts in the Middle Tithonian, the latest Jurassic. This is an Isopac map for the Thamama group, which includes the API 8 sequence with super sequences 1 and 2. And the thickest Cretaceous is found in older Jurassic basin centres, for example, northeast Iraq and Luristan, and in Oman, Abu Dhabi area in the southern part of the Gulf. And we can see the existing influence of structures, for example, the Qatar Dome, the Gawa structure, and the Burgan High controlling isopacs in the Cretaceous. So this is a chronostratigraphic diagram that covers much of the southern Gulf, from southern Iraq in the north, Kuwait, Saudi, Bahrain, Qatar, through UAE and Oman in the south. And we see the same basic stratigraphic architecture, these super sequences separated by unconformities, lower ones passing into clastics towards the west, and generally onlapping the Arabian Shield towards the west. Now, what I want to do for the rest of the presentation is to focus in on 4 case histories. I'm going to have a look at the Ratawi limestone shale, which is an early interaction between clastics and carbonates associated with the K30 flooding surface, so that's Valanginian in age. Then I want to look at a more pure carbonate system, which is the Schweiber shelf carbonates and the Bab intrashelf basin. That's associated with the K80 flooding surface of Aptian age. Then I'm going to be moving up into the Mauddud to look at a reservoir scale case history associated with the K110 of late Albian in age. And then I'm going to be looking at the Mishrif carbonates associated with the K140 around about the Cenomanian Turonian. And I want to focus in on the middle, this large unconformity, the top Mishrif unconformity. And then I'm going to finish off the webinar by discussing briefly the later AP9 supersequence of the Cretaceous. Okay, so that's the cue, my cue to change to Stratbox. Okay, Stratbox is a software package that allows you to present and annotate any sort of data. And here's an example where I've shown some maps. These are subset of the main maps, and I've been able to display these rather than the whole map, because I can select areas at a high resolution and can zoom in. So before I talk you through the details of the case history, I just want to point out a few things about our maps. The blue ornament means carbonates, and the lightest blue means shallow water facies. So that's where you'd expect to find the shallow water high energy facies. Medium blue is lower energy carbonate, dark blue is lowest energy carbonate, and the grey is deep water low energy carbonates, in this case deposited in an intrashelf basin. The orange through yellow coloration means clastic depositional environments. So essentially the orange through dark yellow, pale yellow means continental through shallow marine clastic systems. Now, if we zoom in, we can see we've annotated the maps with various descriptions. We post the information, sedimentological information on wells and at outcrops, whatever data we've got, and we annotate, and you can see in some cases we have these abbreviations. Those refer to actual papers that are published, so you can go straight back to the published paper if you have a query about the data point. So wherever possible, we've tried to justify our interpretation by direct reference back to published papers. Okay, so if we now think about the Ratawi case history, this is a low stand map of late Valanginian age to the K40 maximum flooding surface. This area is an area of karsted carbonate with the exposure of the Ratawi limestone, and the only area of deposition is around the margins of the intrashelf basin. So we've got deeper water carbonates surrounded by an exposed and karsted carbonate platform. And we have a core log from here showing the Ratawi limestone with various brecciated intervals and cavities of karstic origin within it. And we can show a core photograph from this, where we have, this is the in situ carbonate, and it's been cut by these large cavities that has been infilled by a glauconitic sandstone derived from above the unconformity. So that's the low stand. If we then go to the transgressive systems tract, that map immediately follows on from the low stand map. During the low stand, there was a large influx of clastic sediment to the area. So we have these progradation of continental and shallow marine clastic systems. And during the transgression, these clastic systems were reworked in a marine environment. So we see an interbedding of marine shales and biturbated sandstones deposited around wave base. And this is the depositional model for this interval. We have these sandstones that have been reworked in a marine environment, passing out into a muddy marine shelf. Now, moving up through the succession, we now go to from the transgressive systems tract to the maximum flood. So we have much deeper water established over the area, with distal marine clastics interfingering with deep water carbonates, and further out in over the plate into an intrashelf basin where we have deep water carbonates deposited. Now this is an example of a sedimentological log through these transgressive sandstones. So we have these typical coarsening upward sandstones, which are then abandoned, and the tops are either bioturbated or cemented. So these are the low stand fans that were reworked during the transgression, and then during the maximum flood they get abandoned, and we get a low energy marine environment developed over the area. So this is the general depositional setting, where we get these transgressive sandstones, sand bodies, progressively reworked and then drowned, and then the maximum flooding comes on top. During the maximum flood to high stand, the clastic systems are drowned, which gives the opportunity of some carbonates to grow in certain areas of the shelf. So there's actually quite a lot going on in these facies belts. These represent the third order systems tract, but there's probably quite a lot of facies variation within this, and there's also probably higher order cyclicity controlling the deposition of facies throughout this. If we look now at the high stand, we get general condensation of the shelf with some distal marine mudstones, and again areas of carbonate deposition where the shelf is starved of clastic sedimentation. And this is the general depositional model. This clastic sedimentation is fed in by delta lobes at various points along the basin margin. So where you get progradation of a delta lobe in the shelf in front of it, that will cause poisoning of the carbonate deposition. But where you get delta switching, where the river goes somewhere else, you get condensation of the outer shelf and removal of the clastic source, so you get localized areas of carbonate deposition. Okay, let me go back to the PowerPoint. Okay, the next case history I want to look at is in the further south in the Gulf area. I want to look at the Schreiber shelf carbonates and the associated BAB basin. So we're moving up stratigraphy to the late Valanginian Aptian, and this is the early Aptian high stand to the K70 maximum flooding surface. And this really represents the lower Schreiber formation, and it's really the last of the Thamama ramps. So these are ramp carbonates fringing this depression in the shelf. And after that, you get the development and strong differentiation of the carbonate system into carbonate platforms surrounding this intrashelf basin, which is called the BAB basin. And there's much reservoir potential in the platform margin carbonates surrounding the basin. So this would be the white pale blue line that represents the high energy facies with the best reservoir quality. And this consists of rudist rudstone and framestone, with the colonization of the high energy areas of the shelf break with rudists, and also associated bioclastic packstone, grainstone reworked locally from the rudists, and then passing down dip into lower energy facies such as this Orbulina packstone, and then mudstone, and then into more argillaceous facies. And the BAB basin also provides deposition of source rocks. So we've got a clear association between source rocks and reservoir facies here. So I want to look in a bit more detail at the evolution of the carbonate platforms and the intrashelf basin. And in the next 3 slides, I'd like you to pay attention to this part of the map, and I want you to look at how the positions of the basin margin change They backstep during a transgression and maximum flood, and then the carbonate platforms prograde into the basin again during the subsequent high stand. And we can see evidence of this progradation. This is time slice mapping by Pearson 2010, and these lines represent strike lines along cliniforms that represent periods of progradation of the basin. Again, these are probably higher order responses to the sedimentary system, and we can't really map individual cliniforms on this, but we can note areas where cliniform progradation takes place. And this is the depositional model of the transgressive part of the system. It's a carbonate ramp that goes from intertidal areas. So these green areas on the map are the shallowest water carbonates, peritidal facies, and these pass outwards into a mid ramp with algal patch reefs, and then into deeper water, into intrashelf basin carbonate muds. So pay attention to this part of the map and see how these facies belts change. So that's the late Aptian maximum flood to the K85 maximum flooding surface, and you can see the basins widened because the carbonate systems have stepped back in deeper water. And now we've switched to the high stand, and you can see the basins narrowed again. So this is a reflection of the progradation, which we show by these arrows, of the carbonate systems into the basin. And we have a slightly different facies model during the high stands. These are much more open marine with algal and rudist caprinid biostromes around the margins, passing out into a shelf area with rudist patch reefs, and then again down dip into the intrashelf basin carbonate muds. Now, I want to show you something about how spectacular these cliniforms are. This is a time slice mapping near the top Schweiber reservoir of the Buhassa field in UAE, and it represents this red line through here. And we can see all the different facies in the components in the carbonate system. We have the platform interior here, and with these structures which are probably rudist patch reefs developed over the carbonate platform interior. We have the northern margin of the Bab Basin here, and these lineaments are showing the top of the cliniforms as they dip into the Bab Basin. And this is the Bab Basin with the intrashelf basinal carbonates with the no seismic character. So that's the deep water facies. And also, if we look at other seismic attributes, for example, we can see amplitude anomalies or variations of amplitude along the strike of these cliniforms, and you can make inference about facies variations and variations of reservoir quality along these cliniforms. So if this interplay of intrashelf basin and fringing carbonate platforms produces some very complex stratigraphic geometries, and we find that in cycles, Aptian cycles 2 to 4, which are different stages of the Schweiber deposition, we see mainly aggrading to prograding development of the surrounding carbonate platforms. But the Aptian 5 depositional cycle, this is an overall low stand where the carbonate platforms surrounding the Bab Basin become exposed, so you get incision and introduction of plastics along these into the basin at this stage, and you get severe restriction of the accommodation space in the intrashelf basin. So the carbonate system not only downsteps, but it strongly progrades as well. Okay, I now want to go further up in the stratigraphy into the late Albian and look at the Mauddud carbonate interval. And this is a reservoir case history. Okay, so I have to quit PowerPoint and go back into Stratbox. So we're looking at the northern end of the Gulf around in the Burgan field in Kuwait. And this is based on a paper published by my co-authors with me as a co-author on the Mauddud formation in the Burgan field. And this is quite unusual because the Mauddud reservoir is a very thin carbonate reservoir, not more than about 10 meters thick. And as soon as you go into northern Kuwait and north of this line, it thickens dramatically up to about 450 meters. And we have a core log from the Burgan field, where we see a lower clastic unit. This is the Mauddud sandstone formation or member, and this was deposited in a series of prodeltaic and shallow marine environments that were prograding in from the Arabian Shield to the west. And then we have a maximum flood. Sorry, the sandstone, lower part of the sandstone, sandstones in the lower part of the core refer to this map, and the carbonates in the upper part of the core refer to this map. So that goes from the transgressive to high stand part of the system. And during when you get a high stand, high sea level, you drown the clastic system, so that turns into you allow the carbonates to be produced over the shelf. So, and the very top of the Mauddud is quite a marked karstic surface with these rather ornate structures infilled by the overlying glauconitic sand developed at the top of the Mauddud. Now, the question we were trying to address in our paper was, what is the controls over the reservoir quality in the Mauddud carbonate member, and how would you address developing such a thin reservoir? And we found that the Mauddud member over Burgan consists of 2 depositional cycles, probably 4th order cycles, each of which are punctuated by a period of karstic exposure. And we found that the reservoir quality is controlled by depositional facies. It's best in the higher energy facies, and in this case it's also been modified by additional leaching and the development of cavities during these periods of karstic exposure, one in the middle of the Mauddud and the other one I just mentioned at the top. Okay, let me go back to the PowerPoint now. Next case history I'm going to talk about is about the Mishrif Formation. This is Cenomanian-Turonian carbonate unit associated with the K130, K140 maximum flood. And I'm going to talk about, first of all, the depositional facies and environments of the Mishrif, and then I'm going to talk about the effects of the Middle Turonian unconformity. So the Mishrif Formation is the main producing horizon associated within the K132 high stand in Iraq. And this is the palaeogeographic map of the K132 high stand. And the main reservoir quality is found in rootstone and grainstone sand bodies dominated by rudist debris along the shelf margin. So again, it's these zones here, the shelf margins surrounding the shallow water carbonate platform and the intrashelf basins through here. And we find there's local structural control on shelf margin, and Often the reservoir quality is fairly straightforward, nice open primary porosity systems with not much diagenetic modification. So you can relate the reservoir quality directly to the depositional facies. We look a bit closer at the depositional systems. This area, this ridge-like structure, represents this carbonate platform through the center of Iraq, and this cross section represents the same thing. So this Mishrif Formation high represents this cross section through this carbonate platform with shelf margins at either side. The basin to the northeast is an open marine basin, so that's connected to the main near Tethys Ocean, so that whether it's high stand or low stand, that remains open marine. The basin to the west is up against the Arabian Shield, and that is a marine basin during high stands, but during low stands it gets very restricted, sometimes with the development of evaporites in it. Now, the main reservoir facies are a series of rudist shoals, as we've seen, similar to the Schweiber, with shoal development and rudist patch reefs development developed along the main margin. During low stands, the main carbonate platform becomes emergent, and you get karst development over the carbonate platform, with, as I mentioned, restriction in the basin to the west. If we move to the southern part of the Gulf, again, the Schweiber is the Mishrif is a similar producing reservoir associated with the margins of the Shalif Basin in the southern Gulf. The Bab Basin changed its name during the Cretaceous, so it's now called the Shalif Basin. The western margin is stratigraphically more or less complete and shows nice lateral progradation with the usual facies development of rudist grainstones and patch reefs at the shelf margin, passing down dip into lower energy facies with poor reservoir quality. But the eastern margin of the Shalif Basin is very strongly modified by erosion, and the erosion is expressed by the white area on the map. And the topmost beds are missing. We can just see the bottom set beds of the cliniforms at that margin of the basin. So, okay, I'll want to explain in more detail about the impact of the top Mishrif unconformity, and I need to go back into Stratbox. Now, I'll start up here. This is a paper published by Kathy Hollis, who mapped the amount of erosion through the Gulf area, so Oman in the south, UAE through to Kuwait and Iran, showing that there was fairly major erosion in the central part of the central to northern part of the Arabian Gulf, decreasing to the south and to the east. And she demonstrated that it cuts down through these various Cenomanian sedimentary sequences. And also she demonstrated that the effects of exposure have a significant impact on reservoir quality. So here's a poorer perm plot from Sabria Field in Kuwait, and we have the good reservoir plotting at the high porosity, high permeability, and as I mentioned previously, this largely preserves the primary porosity associated with the depositional environment, and we have poorer reservoir quality where we get cementation. Now, the effects of exposure associated with this unconformity varies according to depositional facies. In areas of good depositional reservoir quality, it tends to be beneficial in that the limestones are originally high porosity and tend to allow dissolution. But in other areas, it tends to have a more detrimental effect of porosity where you have lower energy facies. So, for example, if we, the main area I want to focus on in this map are these areas which really show how much of a hole this unconformity punched through the Cretaceous succession. Now, if for example we take this map, which is the Middle Cenomanian Transgressive Systems track to K135, and zoom in on this area, we can see that the actual unconformity cuts across a number of facies belts. The green is this peritidal carbonate. The blue is the high energy carbonates associated with the shelf margin. The palest blue is the best reservoir quality. And then we go into these deeper water carbonates associated with the intrashelf basin. Now, this unconformity impinges on these different facies, and it will have a different effect, different diagenetic effect on the reservoir quality. So it's likely to enhance reservoir quality where you have good depositional facies, and it's likely to be detrimental elsewhere. So you can take these maps at different levels. You can examine the distribution of the unconformity at different levels on different Cretaceous sequences, and you can see where the facies belts impinge on the unconformity surface, and that will help you to give you an estimation of the diagenetic effects on reservoir quality associated with the unconformity, whether it's detrimental or whether it improves reservoir quality. Okay, let me go back to PowerPoint. Okay, I now want to finish off with a brief summary of the late Cretaceous AP9 mega sequences. This is an Isopac map of the Upper Cretaceous, and deeper centres are most evident along the north east margin, thinning to the southwest against the Arabian Shield, and we can see that some of the north-south structural grain remains, the Doha Arch, Gawa, and the Burgan High. These all remain as controls on differential subsidence and sedimentation during the late Cretaceous. This is supersequence 5, Turonian to early Campanian. It commences with regional unconformity that I've just discussed. The initial Turonian is deposited very locally in various intrashelf basins, and the reflooding of emergent areas commences later in the Turonian, commencing in the northern part of the plate. And there seems to be evidence of major structuration during the Coniacian, with the development of major high relief north-south paleo highs. And then we have the onset of rift development, possibly strike slip component due to changing intraplate stresses during the onset of compression. So this is also the stage where we go from the southern margin of Neotethys being a passive margin to a convergent margin. And this palaeogeographic map shows the mid-Santonian high stand to the K160 flooding surface, where we have much of the elevated areas are unlapped by these very large carbonate platforms. Some reservoir facies are developed, and there's some source but seal facies are often complex and often quite localized. This is a summary of supersequence 6, late Campanian to Maastrichtian age. We see evidence significant sedimentary tectonism due to the onset of ophiolite abduction at various points along the plate margin, and also the development of very deep, probably transtensional basins. We still have widespread carbonate facies on the Arabian side of the plate, and locally we have very thick carbonate platforms on the active northeast side of the plate where we have depositional highs. So this is the late Campanian high stand to the K180 maximum flood. And then the central part of the area is a zone of deep water deposition with marls and becoming very, very condensed towards the end of the Cretaceous. Supersequence 6, this is late Campanian, again late Campanian Maastrichtian. We also see various points of entry to the basin of major flysch systems, so clastic systems here, sometimes up to 2 kilometers thick. So this is the time when the collisions really getting, the convergence is really getting going. And there are local low stand carbonate platform systems within the basin systems, and these seem to have a significant reservoir quality in Iraq and also eastern Syria. So when you get a low stand, the carbonate communities migrate to deeper parts of the basin, which are now shallow water, and create their own shallow water carbonate systems. And when sea level goes back up, they get drowned and the area reverts to deep water deposition. Also, again, with the convergence, the connection to the open marine ocean is getting a bit restricted. So sometimes we get evaporites appearing in low stand or transgressive systems tract within certain intrashelf basins.
Thank you, Peter. And could you tell us a little bit more about the course? What's going to happen during the course?
What we're going to do is we're going to have a 5 times half-day course, so that's 5 half days, looking at these case histories that I presented on Stratbox, looking at them in a bit more detail, and also presenting other case histories on Stratbox. And we will be also, I'll be presenting workflows, relevant case histories to try to explain the Cretaceous systems in more details, and also to show you the workflows to try and understand these. And I'll be covering core logging, carbonate facies, diagenesis, seismic expression of carbonate systems, and log data as well.
Okay, I think Gabriela has a question.
I do, Peter. There is a question that's come in from a LinkedIn user. I will try and give it to justice. So thanks, Peter. One question: what is going on in Ras Al Khaimah, and especially beyond towards the east, where the faces are quickly becoming basinal? Do we have a sharp transition from platform to basin? Do you think we still have platform faces beneath the Hajar Mountains?
That's a very difficult place to work with. As far as we can tell, at the moment our maps are showing mainly basinal facies, but that is an area we need to look at in more detail. The problem is once you get into that part of the plate, you have to look below all the ophelites and all the structure that's developed. Evidence suggests that we probably don't have a sharp transition from platform to basin, and I think the actual position will change through time as the carbonate production varies, and also the structure of the margin evolves. But that's something we are going to have to look at in more detail.
Okay, thank you. Thank you, Peter. And I have another question here, which I'll just again put up on the screen. That should be moving away now. Yep. Okay, so thank you, Peter. You showed that the last Schubeck cycle downstep dramatically into the intrashelf basin. Is this a stranded cycle with lateral seals, or is there connectivity to the other clinoforms?
I think you'd have to look at your own data set to answer that question. It's the answer is possibly both, but I think it might depend on the very local geometry of the BAB shelf margins of the sequence 2 to 4 cycles. So I think you probably have to look at your own data and try and map out the geometries in that case.
Okay, thank you, Peter. I don't see any other questions on here at the moment. There may be others that come through at a later stage. So it would be possible for people to post further questions, perhaps in the webinar that we're having this afternoon. There'll be another webinar this afternoon, won't there, Peter, to catch the next time zone. So that's at 3 p.m. UK time. And it will be the same content, but there may be other questions that would originate, so you could have access to that as well. Oh, actually, no, there is one more question that's just come in. Sorry, just give me a moment while I read that out and put it on the screen. Here we go. So thanks a lot, Peter. One additional question. What would be the differences or similarities with the other side of the Tethys-like Burgonian facies?
I don't think that there would be too many differences, because we are just opposite sides of the same ocean. We're in the same faunal zone. So I think you'd have to look at the sort of local tectonic configuration of the basin, which probably would have more influence on the facies patterns. But I think you'd be essentially dealing with the same bioclast assemblages and general carbonate systems. Okay, great. Thank you, Peter. Perhaps we'll give it a few more minutes because some more questions might come through.
I have a question for Peter.
Okay.
And this is more like a kind of a personal question, Peter.
Mm-hmm.
What got you so interested in carbonates and becoming an expert on carbonate reservoirs? What's your story there?
Well, I did my PhD at, go back further. My undergraduate degree was at Leeds, which was a very strongly structural department, and we did some clastic sedimentology, and we had 2 lectures on carbonates, 2 weeks on carbonates. So I just thought, this is something I need to find out more about. And a PhD came up at Manchester on carbonates, which I was very interested in. And at that time, carbonate sedimentology wasn't really as developed as clastic sedimentology was. So I felt there was a real opportunity to sort of push the subject along and do research in it that with perhaps a different slant that a few people had thought of before. And also at that time, there was great interest in the Carboniferous limestone of the UK, the Dinantian, and there was quite a strong group of researchers working on the Carboniferous limestone. I was one of them. Andy Horbury, my colleague who did much of the regional work on the maps, was another one. And we're basically a sort of group of people who knew each other, were all working on the Carboniferous limestone. So there was a sort of nice environment and atmosphere to get started. So and it all sort of started from there.
Okay. Thank you. Thank you for sharing.
You're welcome.
Do we have any more questions, Gabi?
Not that I can see come through at the moment. Just obviously thanking you for your time, Peter, for an interesting
Thank you.
for an interesting webinar. But no, there doesn't appear to be anything else. So I don't know whether you want to hold on or you want to wrap it up.
I think as Gabriella said, there'll be opportunities to ask questions through the LinkedIn website or contact us personally. So if you can think of any other questions, we're happy to answer them. But I'd just like to say thank you to everyone for their time and attention, and I hope I've made a useful contribution to your day.
Thank you very much, Peter.
Yes. And we look forward to seeing you on the virtual workshop later on.
Great. Thank you so much. Thank you, everybody, for your time. Have a good day.
Thank you.